Andrew Holmes, who unfortunately can't be here. And he's going to tell us about chemistry and materials research for the public good. And Andrew's joining us from Australia. Thank you. Nice to see you, Andrew.
Hello, Judith. Thank you very much for the introduction. And hello to everybody who's there in Russellhamer. Best wishes from me and my wife, Jenny, and to everybody online. We're very sorry not to be able to be with you. Congratulations to Professor Ben Feringa on being awarded the Dresselhaus Memorial Lectureship, and to Sir Anthony Cheetham for the Sheikh Saud International Materials Prize. My talk is very loosely about chemistry and materials research for the public good. You'll see that the looseness goes to ideas and also to a bit of biology, but I thought I'd talk about curiosity-driven research in a time in the world when there is big pressure on work that has impact of various sorts. Historically, of course, research was done by largely rather wealthy gentlemen for the pure sake of curiosity, and learned societies emerged, and work was sponsored by people with wealth and people with curiosity and learned societies. But around the time of the Industrial Revolution, industry took over a lot of research, and much of it was centered in the industrial environment. That was moderated, of course, by the events emerging from war, when governments decided they needed to prosecute research for their own benefit through national agencies, and that historical relationship survives now, where we have this balance. We don't have, I think, the rich, largely gentlemen doing it, but I would say that scientific research as a curiosity-driven research is an important aspect of a civilized nation and adds to the body of knowledge. Someone who spoke about this quite a lot was J.D. Bernal. For those of you who have not come across J.D. Bernal, he was known as the Great Sage, and Max Perutz in the Cambridge University Press book, Cambridge Scientific Minds, describes him as an Irish Catholic converted to communism, a mineralogist who had turned to X-ray crystallography. In 1936, I asked Great Sage, "How can I solve the structure of life?" And he replied, "The secret of life is in the structure of proteins. And there's only one way of solving it, and that's X-ray crystallography." So I became an X-ray crystallographer. And we called him the Sage because he knew everything from history to physics. And he, of course, supervised some very distinguished crystallographers, in particular Dorothy Hodgkin. There's a lovely biography of Dorothy Hodgkin which describes the relationship between her and crystallography, and her, as a consequence, the influence of J.D. Bernal. Another interesting thing is that Bernal was a wartime scientific advisor to Eisenhower and other military leaders. So it seems that he managed to keep his political thoughts separate from his scientific advice. But he wrote a book in 1939 called The Social Function of Science. And in the preface, he pointed out, as I've just said, that science has ceased to be the function of curious gentlemen or ingenious minds supported by wealthy patrons, and has become an industry supported by large industrial monopolies and by the state. This book will, however, have served its purpose if it succeeds in showing, I can't read what that is, that this is a problem, and then I have to remove my you can read it, I can't read it all, but essentially saying that this problem, a solution to this problem, depends in providing a proper relationship between science and society. So he was thought about it a lot. So I picked out a few examples, and I must confess to having had quite an Australian bias in some of my choices. These may be things that people have not come across, and I've been a bit liberal in my choice of curiosity-driven research. But the first one I've chosen is the black box flight recorder, which of course is not black, it's usually orange. But David Warren was a scientist employed by a government national agency, but I point to his interest in the possibility of recording music that led to his idea of inventing the flight recorder and voice recorder, or black box. And he knew there was a problem, so I'm not saying it was the curiosity-driven research was within an agency that wanted to solve a problem, and that was in the 50s. Some people present in the audience will remember that the first commercial airliner, the de Havilland Comet, had some serious crashes, and this problem had to be sorted out. And this is where Warren thought having a voice and flight recorder would help detect what went wrong. I believe the problem with the comet was metal fatigue. So he invented this flight recorder, and Air Vice Marshal Sir Robert Hardingham took it back to Britain and made use of it. But ultimately it became mandatory in Australia in 1960 and later mandated around the world, and particularly by the Federal Aviation Administration. Again, there are others who had the idea of recording flight data, as I've listed, but I think Warren was the first to cause the general revolution to have it introduced in civil aviation. Now, another invention from the CSIRO, or CSIR it was called then, a National Research Agency, was the issue of insect repellents to protect the troops in the Second World War from malaria mosquitoes. And dimethyl phthalate, which we're all familiar with now, I think, as an insect repellent, was developed for that purpose. And interestingly, Her Majesty the Queen visited Australia for the first time a monarch visited Australia in 1954, and he used this product to keep the flies and mosquitoes away from the Queen. And in keeping with CSIRO being a national agency to support industry, it did that without any protection for revenue. And this product was used by Aerogard in an insect repellent. I think now Aerogard in Australia uses DEET, but at that time it was dimethyl phthalate. I think one of the great inventions, again coming out of CSIRO in Australia, was the polymer banknote. And the motivation here was that in 1967, or just before that, in the late 60s, currency in Australia had been forged, not quite well actually, but sufficiently. There were some mistakes made and it was detected, but it became urgent from the governor of the Reserve Bank of Australia to invite CSIRO to develop a banknote that couldn't easily be forged. And David Solomon and his team in CSIRO were setting about the problem of solving the idea of generating a polymer-based banknote. And ultimately they designed a multi-layer polymer, multiple layers of a polymer based on, well, the main polymer layer was biaxially oriented polypropylene, and then you'll see there are other layers of low-density polyethylene on either side of a couple of layers of the oriented polypropylene. And they got quite excited in inventing lots of security devices, optical devices, many of which didn't ultimately end up in the final product. But the final product contains intaglio printing. Intaglio is the feeling you have when you put your hand on a banknote that you can feel raised printing images, holograms and other images visible under UV or IR light. And this has become a great success in Australia. It reduced forgery significantly, and also as a consequence, the polymer-based banknotes have much longer lifetime than paper variety. And now the technology has been taken up in a number of countries. Interestingly enough, the EU and the US have still resisted that trend, but the UK has come round to it, Canada, China, Russian Federation, Hong Kong, Israel, and 30 other countries. It looks like this in these photographs here, and if you look carefully at the note, let's take this blue one here, you'll see the first two digits actually are the year in which it was printed. I haven't got any to show you online, but if you put one of these banknotes under UV light, you'll see a hologram, at least with the digits reflecting the dollar value of the currency. And there are many other protective devices embedded. It's really quite a significant transformation and had a big influence around the world. That one, I think, is revenue generating. And the blown polypropylene is done over a big vessel that blows it out like a balloon. And the company that does that is Innovia Films, based up in Wigton in Cumbria, Melvyn Bragg's hometown. And there is the printer here in near Melbourne, where the banknote, the first layers, there's a TiO2 white layer put on first, and this is the printer that delivers that. So it is, as I say, they're a license to print money. Now, this is a story about Wi-Fi, which may not be well known, but John O'Sullivan was a CSIRO scientist in the radio astronomy division, clearly curiosity-driven research. And he and his team in 1977 developed a technique for sharpening and improving the picture clarity in radio astronomy images. And following on from that in the 1990s, he led a team which patented in 1996 the use of a related technique for reducing multipath interference of radio signals transmitted for computer networking. Now, that technology is embedded essentially in every mobile telephone device as the 802.11 Wi-Fi protocol. And essentially, it distinguishes the signal bouncing off the walls inside a room from the actual main wireless signal. And it's incorporated in all Wi-Fi devices. CSIRO took out action against manufacturers and won the case and earns over so far $430 million in royalties. So you see this shift from being a national agency not protecting its intellectual property has been dramatic, and it now expects to earn billions of dollars from continuing revenue after lawsuits settle. Let's move into a bit of biology. Fred Sanger developed the technique for sequencing DNA, in which he, and this is his second Nobel Prize for chemistry, in which he incorporated the, use a primer, of course, to start the copying from the 5' end to the 3' end of the template DNA in the presence of DNA polymerase, and put in the building blocks. These are the deoxynucleotide bases, the 4 bases. They're there in abundant form, but also small amounts of the dideoxynucleotide bases, in which the 3' position, that's the OH position on the 5-membered ring, was missing. So there was no OH there. And so if these were incorporated, the chain growth stopped, terminated further growth out in this direction. And the idea was that for relatively short chains, you could get statistically the copy of the template according to the base incorporated of all the bases present in the original template through this copying process. So you would end up with fragments, they'd stop growing, and each one would reflect the last base in the sequence down the chain. And then by gel electrophoresis, you could separate these. These all had fluorescent tags on them. So by fluorescence detection, one could identify the complementary base at the end of each of the growing chains. And so you wouldn't get a display on a chromatogram from the gel electrophoresis. It gave a readout, essentially, of the complement of DNA. And that essentially, as an automated technology, which is the one that was used for human genome sequences. Brilliant idea, but as you'll see, compared with what's emerged since, relatively slow. Well, that was certainly curiosity-driven research in Sanger's case, and so was the next example, which was work by my former colleagues in Cambridge in chemistry, David Klenneman and Shankar Balasubramanian, who wanted to speed this up by massively parallel next-generation sequencing, in which they measured the effect of each base being added in real time, so to speak. So the genomic DNA was fragmented, and then they used adapters, which is essentially like a motor, and they ligated that system to a solid state, and then it undertook cluster amplification. And then this is loaded on a flow cell, and the fragments are hybridized to the flow cell that I've just said. And each bound fragment is amplified into a clonal cluster through bridge amplification. So essentially, what they're doing is watching bases being added, but again, they incorporated cleverly bases which at the 3' end could not go on once they were incorporated, and which had a long chain with a fluorescent probe attached. So once this is incorporated, the growth is stopped for a short time. They can image it, and this will be the complementary base to the chain that's being grown, the complementary base added as it's growing. And then by simply reduction of these azide groups, in each case, this azide and this azide, the free OH in the 3' position, and the nucleus, the fluorescent probe, are removed. So it's added by growth, fret detected, and then taken off, so the next chain, next building base can be added on sequentially. And this is done on a chip, base by base, on a massively parallel scale, using fluorescently colored nucleotides, which are added by a DNA-type polymerase exercise. And then the alignment is carried out against the reference genome so that they can read the sequence. And this is super fast, and the Q-score, which measures the base readout technology, corresponds to a 99% base core accuracy. It's cost efficient. The company they started was called Solexa, which eventually became taken over by Illumina. And curiosity-driven research started in a pub near the chemistry department in Cambridge called the Panton Arms. And I like this picture in one of the articles they wrote, in which Shankar and David are having a pint, which is where they had the original idea. And Shankar says, "I once told the landlord that I'll make him very famous one day." I think that's a great story of curiosity-driven science. And of course, the Illumina technology started off being used very much for personalized medicine. So one could screen, for example, the genetic sequence and genomics of a particular type of cancer, and then use the best anti-cancer agent for that particular genetic sequence. But I imagine it's this most recent sequencing in the pandemic that has really revolutionized the fact that, well, we've given it up in Australia. I don't know what's happening in the rest of the world, but when we were trying to have zero COVID, we were having sequencing through the PCR screening of all the COVIDs on a selective basis to see whether any new variants were emerging and how they were progressing in the population. Well, since then, nanopore sequencing technology has emerged, and I'm going to have to speed up a bit, but here a protein nanopore is embedded onto an array of microscaffolds, 2,048 nanopores on the chip, and a motor protein slows the speed of the unraveled DNA, so the single strand is fed through by electric charge, the negatively charged DNA being pulled through to the positive side through this membrane. And the electrical readout, because there's an insulator here, a sensor below it, an electrical readout gives a characteristic signal for the type of nucleic base passing through in a continuous flow. This is really fast, and I think will emerge with refinement ultimately as the technologies, preferred technology you see here, capable of sequencing 450 bases per second. Now, the disadvantage is that the advantage is you can record thousands of current measurements per second, and you use machine learning, which I think we should note is really going to influence the way in which science develops and is influencing science in the future, to learn to read out the sequences. So it can do ultra long reads. It's relatively high error rates, 16 to 15% compared with the Illumina 1.1 to 1%. And you need relatively large amounts of material. But there it is. It's really, I think, going to emerge because of its power of large and rapid readouts. And you can go forward through one strand and back through the other strand from the 3' to the 5' end and back to do it. Now, how much have I got, Judith? Have I got a couple more minutes? I'm not sure if I can hear anyone, so I'll stop till you stand up and shut me up, Judith. I want to mention Martin Green's work. We call him in Australia the father of silicon photovoltaics. And through a period of work from the 1980s right through to the present time, he's been optimizing and improving the efficiency of silicon photovoltaics. I'll skip to the PERC cell, which is the one that's now 90% world production, 2020, $130 billion US sales, and that the PERC cell uses a doped back cathode here, boron doped. This is the Pearl variant of it, but these are all PERC cells of various variations. And this is certainly curiosity-driven research, but with a motivation to have something which ultimately humanity needs and is using. And I suspect that the greatest influence has been a couple of a number of his senior co-workers were Chinese scientists who went back with a determination to make this a cheap and productive and reproducible technology. And it certainly is. It's now reduced the cost of silicon photovoltaics. I'll skip through just two more stories, one on semiconductors.
And Andrew, you have
yes.
it's fine. You have another 5 to 10 minutes, so don't hurry. It's good.
Oh, thank you, Judith. That's good. Well, this photograph of Higa, McDermott, and Shirakawa was actually taken before the 2000 Nobel Prize was awarded at a conference on synthetic metals, and they invented the field of synthetic metals and created this biennial conference. But people felt these people must get the Nobel Prize pretty soon, and lots of photographs were taken at this conference. And sure enough, in the following October, they did. And McDermott spent his life working with non-metallic species which behave like metals. And on visiting Shirakawa, McDermott and Higa were collaborating on silicon nitride, sulfur nitride, polythiazine, polysulfur nitride. And McDermott knew that if you doped that, it became more conducting, if you doped it with halogens. But when he saw what Shirakawa was doing with metallic, silvery-looking polyacetylene, which had been made by a Ziegler catalyst in which they used far too much catalyst, he persuaded Shirakawa to come and work at Pennsylvania, where Professor Klein was also at the time, or subsequently, and they collaborated with Higa, and eventually they found that doping polyacetylene with halogens or arsenic pentafluoride improved the conductivity from about 10 to the minus 6 Siemens per centimeter to 560. And they went on and used stretched polyacetylene and got intrinsic conductivities up near metallic copper. And it's because you have this a radical cation, if you like, over about 15 repeat units, which is able, through charge mobility along the chain and through pi-pi interactions between the chain, to become a conductor from being an insulator. And metallic and organic semiconductors, well, I'll go on and say P.PSS is really, I think, still the best commercial conducting polymer. And this is both protonically doped and also, again, oxidatively doped by forming radical cations. And it was used by AGFA for an antistatic coating, huge quantities. Its typical conductivity is up to 4,500 Siemens per centimeter. And it's a really useful alternative to metallic electrodes. It was also made by Bayer. Bayer and AGFA were jointly working, joint partners in the same company. And semiconductors on the polymer scale have gone into flat screen TVs. And I think others might talk about that later on. And the reverse of putting charge into a polymer and getting out light to putting light into the polymer and getting electrical charge out has meant that polymer solar cells are now up at the efficiencies of silicon that's used in commerce. And I think Professor Sir Anthony Cheetham will talk a bit about perovskites in his talk. So there's the solar cell. I'm going to skip through the lithium-ion battery just to say that Whittingham did start at Stanford, so it was curiosity-driven research, but used lithium at Exxon. John B. Goodenough at Oxford in 1980 realized he could make a much higher voltage by using lithium ions in cobalt oxide, and that went up to 4 volts. That started to really get significant power. and then Yoshino, industrially driven here, replaced the lithium electrode, which of course could catch fire by petroleum coke. And finally, I draw your attention to some brilliant curiosity-driven research in separating the telescope in the James Webb Telescope from the rest of the equipment, because black-body radiation from any part of the equipment would interfere with the very weak infrared signals being collected from deep space, infrared because of time shifting, red shifting of the emission of early stars and other objects. And this Kapton 5-layer aluminium and doped silicon coating keeps the heat away from this, even at the very low temperatures in outer space. And the telescope is made of beryllium coating, which had to be folded up into 18 sections to get into the rocket, and is now unfolded as planned in the solar orbit, and has to be stable at -220. So I'm skipping through that because I know my time is up. I would like to thank His Highness Sheikh Saud and NASA, Dr. Nasser Bustami and the Seven Rock team, and Dr. Natalie Herring and the RACCAM board for making this meeting possible. And congratulations to Sir Anthony Cheetham, shown here with a former Australian High Commissioner in London, Mike Rann, and His Highness. So thank you very much.
We thank you very much, Andrew, for a fascinating talk, taking us all through history and some really great recent inventions and discoveries. I wonder if we have any questions from the audience? Or do we have any online questions, Natalie? No? Okay. I wanted to ask you, actually, Andrew, first of all, about recent advances in performance of organic solar cells, because people are telling me that there have been some very good performance enhancements lately, and I just wondered, you didn't mention anything about that. I wondered if you have any knowledge on that.
Yes, well, on the polymer cells, which people worked on for a long time, and then a little bit of excitement went out of it for reasons I'll mention. Now the polymer efficiencies are up around 18% or more, and we and others have printed large area solar cells. The printing is an issue of engineering alignment, but with encapsulation, I'm sure they will have an application. They've been eclipsed by the perovskites, which I think will be spoken about later, whose efficiencies have gone up into the early 20s. And perovskites, I think, will also be very successful, and there are many groups commercializing these. They are moisture sensitive, and they do have some hysteresis problems, and people have been trying to get lead out of the atmosphere for a long time, and perovskites are lead-based, but the tin ones are coming on, and they're around the 10% or more efficiency now, and they, I think, will eventually catch up. So they've got a very promising future and may well emerge as the preferred technology. Again, we have been involved in deposition from solution, as have others. But that's about the state of play as far as I am aware at the moment, Judith.
Okay, thank you. Tony has a question now.
Hello, Andrew. Can you see me?
Yes, I can. Thank you.
That's wonderful. Well, we're going to talk later in the board meeting tomorrow, I guess. But I wanted to ask you, there are ramifications from what you said for how science is funded in a way, that because many of these most exciting discoveries were not funded by following the mandates of the research councils who want a well-defined path and so on. What are your views on that?
Well, that was what the motivation for the talk, that was my motivation for giving the talk, and I've been involved in the UK Research Excellence Framework assessment on main panel B. I'm not allowed to talk about anything, but it has been very interesting seeing how important impact assessment has become in the UK, and I was interested to see, because we're probably going to do it here in Australia. I don't think it's so black and white, if I can use that phrase, in the United States and maybe not in other countries. But I think many of us are very concerned that research is so imperfect that we only do it because of that and enjoy the discovery of the serendipitous discovery, and then the Pasteur principle of chance favors the prepared mind, and we like to boast that that's our modus operandi, but it's going to be quite hard, I think, and is getting harder for anyone in society to survive on that resource and expectation. So I just put it out. I think I remember when we took technology commercially funded contract research, we always doubled what we were given and used the other half to do curiosity-driven research. That's perhaps one way of doing it, by making the cost of research more expensive, but then the competition may mean that we lose out on the contract. So I do hope governments will realize that, as they are in some countries, that research, curiosity-driven research, as I said, for its ability to add to society's knowledge, is worthwhile in its own right.
Yeah, thank you. This is related to my talk tomorrow, of course, but I'm interested to hear your view on it.
Yes, I hope I decided I wouldn't speak about anything that's being done by people who are involved there in the room and elsewhere. But we heard in the last lecture a perfect example of why it's such an important aspect of research.
Yeah. Thank you so much. Stay well. Bye.
Do we have any other questions? One over here. Okay. Dravid?
Yes, I very enjoyed it, especially the journey through memory lane. You alluded to artificial intelligence, machine learning briefly. Would you mind expanding whether you see it more in optimization or discovery or any other attributes of the machine learning and AI? How do you see it moving forward for materials discovery?
I'm very ignorant. I'm a pot-boiling chemist, which means that I wasn't very good at the aspects of the topic you're talking about. But if you just look at Google AlphaFold and the ability now not only to predict folding of proteins, but also protein substrate interactions, that is going to dominate, I think, pharmaceutical drug design. In chemistry, I know Andrew Cooper in Manchester is using a lot of AI in polymer science design, sort of polymers you're interested in design. And then I read a few papers where chemists are using machine learning for catalyst design. Of course, it's going to be machine learning more, although I think the Google AlphaFold shows that predictive work is going to be possible as well.
Okay, thank you. I think we perhaps should leave it there, and I just want to say thank you very much again to Andy, and we really miss you here, and we hope to see you next year. Thank you very much.
Thank you all very much. Bye.